An adiabatic process is one in which no heat is transferred to or from the system. For an adiabatic process, the value of the heat supplied always equals 0. So our energy equation is written as minus W equals U2 minus U1. We can obtain the PV relation of an adiabatic process for an ideal gas using the differential form of the energy equation. So minus W equals U2 minus U1 becomes minus dW equals du. And for a reversible process, dW equals pdV. So minus pdV equals du, or du plus pdV equals 0. For an ideal gas, du equals m times Cv, the specific heat at constant volume, times dt. So mCv dt plus pdV equals 0. For simplicity, we'll divide through by the mass. So instead of differential volume in the second term, we now have differential specific volume. Remember, our aim is to obtain a PV relationship for an ideal gas undergoing an adiabatic process. The first term in our equation, Cv dt, uses temperature. So we're going to have to find an expression for dt in terms of pressure and specific volume. If we take the total differential on both sides of the ideal gas equation, PV equals RT, we have something that looks like this. PdV plus VdP equals RdT. So for an ideal gas, dt equals 1 over R into PdV plus VdP. Putting this into our equation, we have Cv divided by R into PdV plus VdP plus PdV equals 0. We can multiply through by R, so we have Cv PdV plus Cv VdP plus R PdV equals 0. And this becomes Cv plus R times PdV plus Cv times VdP equals 0. In the previous video, we derived a relationship between the specific heat at constant pressure and volume and the gas constant, which is Cp equals Cv plus R. So in our equation, we can write dividing through by PV, we have Cp dV over V plus Cv dP over P equals 0. And dividing by Cv, we have Cp divided by Cv times dV over V plus dP over P equals 0. Also recall that Cp divided by Cv is defined as the specific heat ratio, gamma, of the gas. So we have gamma dV over V plus dP over P equals 0. Integrating both sides, we have gamma times the natural logarithm of V plus the natural logarithm of P equals a constant value, or the natural logarithm of PV to the power of the specific heat ratio is constant. Taking e to the power of both sides, we're left with PV to the power of gamma is constant. This is the relationship between the pressure and specific volume for an ideal gas undergoing an adiabatic process. It is also the relationship between the pressure and actual volume. Since work done is given as the integral PdV, for an adiabatic process, we can write P equals C divided by V to the power of the specific heat, or Cv to the power of minus gamma. So putting this into our integral and integrating, we have work done equals C divided by gamma minus 1 into V1 to the power of minus gamma plus 1 minus V2 to the power of minus gamma plus 1. Now, since C equals PV to the power of gamma, it can be P1 V1 to the power of gamma or P2 V2 to the power of gamma. So using this, we can obtain our work done as P1 V1 minus P2 V2 divided by the specific heat ratio minus 1. And this is the work done in an adiabatic process for an ideal gas. Also, using PV equals RT, we can derive TV and PT relationships for an adiabatic process for an ideal gas. For our temperature volume relationship, if PV to the power of the specific heat is constant, then P equals C over V to the power of gamma. Substituting into the ideal gas equation, we have CV over V to the power of gamma equals RT, or C over R equals TV to the power of gamma minus 1, which makes TV to the power of gamma minus 1 constant. And for our PT relationship, pressure-temperature relationship, if PV to the power of gamma is constant, then we can rearrange this, making V the subject of the formula, and V equals C divided by P to the power of 1 over gamma. Substituting into the ideal gas equation and simplifying, we obtain our PT relationship as T divided by P to the power of gamma minus 1 all over gamma is constant. We can show a reversible adiabatic process for an ideal gas on a PV diagram, and the shaded area shows the work done. One kg of steam at 100 bar and 375 degrees Celsius expands reversibly in a perfectly thermally insulated cylinder behind a piston until the pressure is 38 bar and the steam is then dry saturated. Calculate the work done. We've been told the cylinder is perfectly thermally insulated, so we can treat this as an adiabatic process. Our energy equation is minus W equals U2 minus U1, or W equals U1 minus U2. To calculate the work done, we need to find the initial and final internal energies of the system. At the initial state, the steam is at 100 bar, or 10,000 kilopascals, and has a temperature of 375 degrees Celsius. From our steam tables, we see that at a pressure of 10,000 kilopascals, the saturation temperature is 311 degrees Celsius. So our current temperature, 375 degrees Celsius, is greater than the saturation temperature. This means that the steam is superheated at this state. To find our initial specific internal energy, we'll use the superheated steam tables. So for 10,000 kilopascals or 10 megapascals, we interpolate between 350 and 400 degrees Celsius to obtain the specific internal energy at 375 degrees Celsius. And we obtain this specific internal energy, U1, as 2,787.1 kilojoules per kg. At the second state, the steam is at 38 bar or 3,800 kilopascals, and it is dry saturated. So its specific internal energy will be equal to Ug at this state. To find Ug at 3,800 kilopascals from our steam tables, we interpolate between 3,500 and 4,000 kilopascals. Doing this, we obtain our specific internal energy, U2, as 2,602.2 kilojoules per kg. So our work done, U1 minus U2, equals the mass into the specific internal energy, U1, minus the specific internal energy, U2. So our work done can be written as M into U1 minus U2, where U1 and U2 are the specific internal energies. And from this, we obtain work done to be 184.9 kilojoules. We have a positive value, which indicates that the system did work on its surroundings. This makes sense because we were told that the process was an expansion process. Air at 1.02 bar and 22 degrees Celsius initially occupying a cylinder volume of 0.015 meters cubed is compressed reversibly and adiabatically by a piston to a pressure of 6.8 bar. Calculate the final temperature, the final volume, and the work done. Assume air is a perfect gas with the gas constant equal to 0.287 kilojoules per kg Kelvin, and the specific heat at constant volume CV equals 0.718 kilojoules per kg Kelvin. We know P1 is 1.02 bar or 102 kilopascals. T1 is 22 degrees Celsius or 295 Kelvin. V1 is 0.015 meters cubed, and P2 is 6.8 bar or 680 kilopascals. We can calculate the final temperature using the PT relationship for an adiabatic process. We can write this as T1 over P1 to the power of gamma minus 1 all over gamma equals T2 divided by P2 to the power of gamma minus 1 all over gamma, which we can rearrange as T2 divided by T1 equals P2 divided by P1 to the power of gamma minus 1 all over gamma. Now, gamma is the specific heat ratio and is given as Cp divided by Cv. But we only know Cv and R, so we use Cp equals R plus Cv. And we obtain Cp as 1.005 kilojoules per kg Kelvin. And our specific heat ratio is 1.005 divided by 0.718, which is 1.4. So substituting all of that into our PT relationship, we obtain T2 as 507.3 Kelvin or 234.3 degrees Celsius. To find the final volume, we can use the PV relationship. So we can write P1 divided by P2 equals V2 divided by V1 to the power of gamma, or V2 divided by V1 equals P1 divided by P2 to the power of 1 over gamma. Substituting all our known values, we obtain V2 as 0.0042 meters cubed. To calculate the work done, we use our derived expression for work. Work done equals P1V1 minus P2V2 divided by specific heat minus 1. And substituting all our values, we obtain our work done as minus 2.56 kilojoules. The negative value means work was done on the system, and this makes sense since the fluid was compressed. The final kind of process we're going to be discussing is the polytropic process. In practice, many processes approximately follow the PV relationship. PV to the power of n is constant, where n is a constant value. Any such process is called a polytropic process. The processes we've discussed previously are special cases of polytropic process. For a constant pressure process, n equals 0. For an isothermal process, n equals 1. And for an adiabatic process, n equals the specific heat ratio, gamma. Since we've already derived the relations for an adiabatic process for an ideal gas, all we have to do for a polytropic process is to replace the specific heat ratio with n. So for an ideal gas, the work done in a polytropic process is equal to P1V1 minus P2V2 divided by n minus 1. The TV relationship is TV to the power of n minus 1 is constant, and the PT relationship is T divided by P to the power of n minus 1 all over n is constant. Now let's solve a problem on polytropic processes. 1 kg of a perfect gas is compressed from 1.1 bar and 27 degrees Celsius according to the law PV to the power of 1.3 is constant until the pressure is 6.6 bar. Calculate the heat flow to or from the cylinder walls. 1. When the gas is ethane with molar mass 30 kg per kilomole and specific heat at constant pressure is 2.1 kilojoules per kg Kelvin. 2. When the gas is argon molar mass 40 kilograms per kilomole, and specific heat at constant pressure is 0.52 kilojoules per kg Kelvin. So, to calculate heat flow, we use the energy equation Q minus W equals U2 minus U1, or Q equals U2 minus U1 plus W. For this process, the work done equals P1V1 minus P2V2 divided by N minus 1. And the difference in internal energy, U2 minus U1, equals the mass multiplied by the specific heat at constant volume multiplied by the difference in temperature, T2 minus T1. For both gases, T1 equals 27 degrees Celsius or 300 Kelvin, and P1 equals 1.1 bar or 110 kilopascals, and P2 equals 6.6 bar or 660 kilopascals. Using the PT relationship, we can obtain T2, and from this we get T2 as 453.6 Kelvin. For ethane, we can find the specific heat at constant volume using the relation Cp equals Cv plus R, or Cv equals Cp minus R. We know Cp, the specific heat at constant pressure. To find R, we use our universal gas constant divided by molar mass, and this gives us 0.277 kilojoules per kg Kelvin. So Cv equals 1.823 kilojoules per kilogram Kelvin. We can now use this to find the difference in our internal energy. And substituting our known values, we have 280 kilojoules as the difference. Now to calculate work done, remember we said work done is P1V1 minus P2V2 divided by N minus 1. From the ideal gas equation, PV equals mRT. So P1V1 equals mRT1 and P2V2 equals mRT2. So our work done becomes mR into T1 minus T2 divided by N minus 1. And substituting our known values, this gives us minus 141.8 kilojoules. Now we obtained our difference in internal energy and our work done. So to get the heat flow, we substitute these values into our energy equation and we obtain heat flow as 138.2 kilojoules. A positive value indicates that the gas absorbed heat from its surroundings during the compression. Now, using the same method for argon, we have our gas constant equals the universal gas constant divided by the molar mass, and this gives us 0.208 kilojoules per kg Kelvin. And our specific heat at constant volume, Cv, equals Cp minus R, which gives us 0.3121 kilojoules per kg Kelvin. So, the difference in internal energy, U2 minus U1, substituting all our known values, equals 47.9 kilojoules. And our work done, mR into T1 minus T2 divided by N minus 1, gives us minus 106.5 kilojoules. So, substituting our change in internal energy and our work done into the energy equation, we have our heat flow as minus 58.6 kilojoules. The negative value indicates that the heat was rejected by the gas to its surroundings during compression. All of the equations we have derived for the processes are shown in this table. Also remember that we only use the ideal gas relationships when dealing with ideal gases.